So next Thursday is the second midterm exam. Who could have thought? It feels like the first one was just yesterday. Yeah, it was much warmer, you know. So next Thursday, November 5th, right here, for most students. As you know, last time we had an overflow, and again, I apologize for this. I apologize to those students who didn't have a comfortable seat. So we'll avoid this situation, this kind of situation. This time we'll have some breathing room. And unfortunately, that means that two sections, students from two sections, those which are led by Dario, will meet at a different, undisclosed location. No, I just didn't want to write it. You can find it. Dario will tell you. If you are in Dario's section, Dario will tell you, and it's also on the class homepage. It's in Barrow's hall. And if you're not in the section of Dario, then you don't need to worry about it. You should just come here, okay? And on the home page, you will find more information, but it's basically the same deal. Someone asked me for the cheat sheet for the page of formulas. Can we use the old one, the one from the first midterm? The answer is no. You have to make a new one. It will also be on one-sided. It has to be one-sided on one side of standard size sheet of paper. Okay? But don't worry, we're not going to test you on the material of the first midterm anyway, so it doesn't make a difference. The midterm will cover the material after the first midterm. Okay, everything that we've done up to now, since the first midterm up to now, up to this week, including this week. And there are on this webpage, you will find problems for review, and you will also find a mock midterm. It's not posted yet. I will post it tonight. The mock midterm. Okay? Any questions about this? About the exam? Next Tuesday, we'll have a review lecture, as before, in which I will discuss all this material and kind of try to put it in perspective, and you will have a chance to ask me questions about it also. Yes? Oh, so there will be no quiz next week. So it's the same deal as last time. The mock midterm, the idea is to give you problems which kind of look similar to what you should expect, of course, yes. Well, difficulty is an eye of the beholder, right? So for some people, it will be more difficult, some people less difficult, but it should be in the same ballpark. Okay? All right. So let's go back to the material of last Tuesday. We talked about triple integrals, and we talked about special coordinate systems for triple integrals, the cylindrical and spherical coordinate systems. Okay, so I want to say a few words, general words about triple integrals. So when I say triple integral, it means that we have something like this, where E is a region in three-dimensional space, something we denote by R3. F is a function, and dv is what we can think of as kind of a measure of integration, which we would usually write as dx, dy, dz, but in some order. But in fact, we know that we can use other coordinates as well. And today we'll talk more about the possibility of using different coordinate systems. So the basic setup for calculating this integral is, as I already explained last time, and as has been explained last week, but I want to repeat it one more time, is that you want to represent this triple integral as an iterated integral. In other words, you want to break it into steps, where at each step you are just evaluating a single integral, an integral in one variable, something which we learned before in one variable calculus. And the way you do it is, first of all, you find the projection of your three-dimensional region. So you have some three-dimensional region here. But the first thing you do is you find its projection on one of the planes, one of the coordinate planes. Let's say xy plane, but it could be xz or yz plane. So that's the projection, D. Let's call it D. So this E is three-dimensional. This is three-dimensional. Whereas D is two-dimensional. It's a two-dimensional region which is in the xy plane. Okay? So once you do that, you can rewrite your integral as an iterated integral, where you have a double integral over D, and here you put dA, which is a measure of integration in the two-dimensional space, which is essentially dx dy. And then you have an integral of f with respect to the remaining variable, where you have to put the limits. So there will be some limits, alpha and beta, which in general will depend on xy. So here xy will be in D, and for each xy, the limits for the single integral will be from some alpha of xy to beta of xy. Now, the way we write it is slightly confusing, and you saw that confusion last time at the lecture when we discussed it. It is important to remember that you read the integral from right to left. I mean, that's the way it's done. It's a convention. You read it from right to left, which means that you first do this one. This is the first step. You first evaluate this single integral, okay? And then, the second step, you evaluate the resulting double integral. So once you evaluate this, you will get something which will depend on x and y. This will be an expression depending on x and y, which you then integrate over D in the xy plane. So we break it into two steps. The first step is a single integral with respect to the remaining variable along which you have projected. And the second step is integrating over the image of the projection, which is D. This is the image of the projection. Okay? So we can actually write it further as a combination of single integrals, because this double integral, in turn, can also be written as an iterated integral. Okay? So that means that writing integral over D, dA, as an iterated integral with respect to x and y, we actually end up with three single integrals. So here we also have a choice. There's a choice. Which one goes first, x or y? Okay, let's say, and what do we mean by which goes first? Which one will appear first, or which one you will integrate first? As I just said, you read it from right to left. So the roles are reversed. Right? So let's write it like this. Let's say it's dx, and then it will be dy, and then finally it is dz, and then you have your function f. Here I wrote f dz, and here I wrote dzf. It doesn't really matter, as we discussed last time. It doesn't matter in which order you write f and dz, or f and dy, and so on. I find this form a little bit more convenient to remember, more intuitive, because the variable of integration is written right next to the integral, so you will not forget which one you're integrating. But the important thing to remember when you look at this formula is to read it from right to left. You read it from right to left, which means that this is the first step. integrate over z. I'm skipping the limits. Of course, there will be limits. For example, here will be limits alpha of xy and beta of xy, like on that blackboard. But let me just skip that. I'm just giving you kind of schematics of this process. Okay. So the first step is integrating f over z. The result will be a function which only depends on x and y because we have integrated out z. Think of it as kind of removing the dependence on z by averaging out over z, over the effect of z. The result is a function of x and y. That function you integrate over y. This is step number 2. This is the second step. And finally, you integrate the result, which will now be only function of x over x, so that the end result is actually a number independent of all of the 3 variables. So at each of the steps, you get rid of one of the variables. You're kind of averaging out over that variable, so that the result does not depend on that variable. If you're doing an integral, and suddenly you notice that you have integrated over z, but the result somehow depends on z, that you carry z somehow to the second or first or third step, you have made a mistake somewhere. There should not be any dependence on z on the second step. There should not be any dependence on y and z at the third step. You see, so this is a very easy test to see if you're doing things in the right way. Okay? Any questions about this? So it's kind of a notational issue, but you just have to remember that you kind of this is because it is actually it is very it makes sense because you're integrating this expression. Okay, but what is this expression? This expression is obtained by integrating this. Integrating with respect to y, this expression. So unraveling it, you see that first you have to integrate this, and you integrate this, and then you have to integrate this. It makes perfect sense that you go from right to left and not from left to right. Okay. Now there is a very special case of a triple integral. There is a special case, and that's the case when the function f, which in general is just any function of x, y, and z. Right? So f is really f of x, y, z. In general, it could be anything. It could be x squared times e to the y times cosine z or whatever you want. But there's a special case when this function is actually just equal to 1. Okay, it's the simplest function you can imagine. Well, say 0 perhaps. But if the function is 0, the integral is 0, so there's nothing to discuss. So let's talk about the case when the function is actually equal to 1. And also, let's assume, in addition, that our region in the 3-dimensional space, E, is the region above this domain D in a 2-dimensional space, under the graph of some function, of a function. Let's call this function f capital. Note that this has nothing to do with f small. F small is a function of 3 variables. It's a function on E, which is a region in 3D, on R3, on 3-dimensional space. But let's suppose that the region itself is, there is some function, so let's draw a picture like this. So let's say D is a kind of rectangular region. And here we have some function like this. So we have this is a graph of a function. So let's say that this is a graph of a function z equals f capital of xy. This. So this is what we discussed when we talked about double integrals. When we talked about double integrals, we discussed the fact that a double integral represents the volume under the graph. The volume under the graph. So the volume under the graph, I put it in quotations. What I mean is, first of all, that I'm assuming that this function is greater than or equal to 0 on D. For otherwise, it would not be above the xy plane everywhere on this region D. This is region D, which is now kind of a rectangular region. I have chosen to simplify things. Okay, and also when I say under the graph, I really mean under the graph but above the xy plane. And also, on the sides, it's confined by the boundaries of D, which in this case are just vertical planes like this. Okay, so when we talked about double integrals, we discussed the fact that the volume is equal to this volume under the graph is equal to the double integral over D of f capital xy dA. Right. So now I want to show that you get exactly this answer if you also by calculating a triple integral, but with the function 1. You see, so this is one of the points which many people find confusing, that the volume under the graph is actually given by double integral, but it's also given by triple integral. But in the special case is that the function which you integrate, function of 3 variables, is 1. In other words, what I'm integrating now is dv. You see, this is the most general triple integral. It's an integral of f dv over e. But now f is 1. So if you want, I can put 1 times dv, but it doesn't matter. 1 times dv is dv. Okay, so what is it equal to? Let's use this formula. First of all, so I project onto d. And in this case, I surely can do that, because my region has a very nice projection onto the xy plane, specifically, because it's under the graph of a function. And so I will have here dA. And then I will have to put the limits here, alpha and beta, and integrate my function. But what are the limits in this situation? In this situation, the lower limit is always 0. I'm always counting z from 0, right? Because the bottom lid of this region is just a rectangle on the xy plane. So that means z is equal to 0 at the bottom. Here, z is equal to 0 across the bottom. So that's why here I actually put 0. And then I'm integrating z from 0 to something which lies on this graph. So that's the sort of the top of this region, right? And so for the top point of that region, what is z equal to? Z is equal to f capital of xy, right? So that means that my upper limit is f capital of xy. And then I have to put f dz, but f is 1 again. So it's 1 times dz, right? So this is very easy to find, right? This is just a very special case of this general setup. I have to take the antiderivative to calculate this integral. I simply have to take the antiderivative of 1. And antiderivative of 1 is z, plus a constant, but anyway, we're going to take the difference of the limits. So it's going to be z with the limits f of xy and 0. So what is that? That's just f of xy. So this inner integral, which as we have agreed should represent the first step of the calculation, this inner integral is simply equal to f of xy, right? Simply because the function is 1. This argument would not work necessarily for a general function. For a general function, we'll have some f here, which depends on xy, right? And so xyz, in fact. So a general function depends on xyz, so you wouldn't be able so easily find the antiderivative. But for the function 1, that derivative is z. I mean, this for sure we know, right? So that's the answer we get. And once we get this answer, let's substitute it here. So we get double integral of f capital of xy dA. So that's the same answer the same answer as before, right? The answer before was the integral of f of xy dA over d, and that's exactly what we got by integrating the function 1 over this entire three-dimensional region. Okay, does this make sense? Yeah? Any questions about this? So the conclusion is that this integral is actually equal to the triple integral over E, where E is this region inside. This is E. E is the three-dimensional region, which is drawn here, under the graph. So, one more time. The volume of this region under the graph can be represented in two ways. One is triple integral, but a very special function, namely function 1. Okay? And can also be represented as a double integral of the function f capital, of which this is the graph, over the region D. The reason why the two things are the same is the result of calculation of representing the triple integral as an iterated integral, where at the first step we very easily evaluate what the result is for this function, for this special function 1. That's what we get. Okay? So now, of course, you can ask, if the integral of the function 1 over the three-dimensional region is nothing but the volume of that region, what about the general case? What about an integral of general function f of xyz? Is this also some sort of a volume? Well, there are two ways to interpret the triple integral for a general function. For a general function, function f of xyz. Not necessarily one, not one, but some general function. There are two ways to interpret. Two ways to interpret the integral. Well, the first way is, let's suppose you want to interpret it as some sort of a volume. And let's argue by analogy. Okay? Suppose let's go down one dimension lower, and let's look at the integral of this function over the two-dimensional region, double integral. This is a double integral, but we interpreted it as a volume of something three-dimensional. You see, so a double integral of a general function actually corresponds to a volume of something three-dimensional, of dimension greater by 1. So you start as a double integral, but you get a volume of something three-dimensional. That's not surprising, because likewise, if you have an integral, a single integral of a function one variable, right? What does this represent? It represents the area of something two-dimensional, namely the area under the graph of this function f. Oh, let's choose a different function notation for this function so that we don't confuse different things, right? So a single integral corresponds to the volume, but in this case we call volume area. That's the terminology, proper terminology. Area of something under the graph of this function, and this something is actually two-dimensional, even though you start with a single integral. If you start with a double integral, so 2 is the number of integrations, you get volume of something three-dimensional, right? So what will you get if you take a triple integral? You get a sort of hypervolume of something four-dimensional, right? So, I mean, if you insist on interpreting the integral as a volume of sorts, you have to you have to introduce one extra dimension, and so you will get kind of hypervolume. I don't know. There is no good term for it. Mathematicians will just call it a volume because you don't care about the dimension. You still call it a volume. But let's call it hypervolume to emphasize that it is a volume of something it's not kind of an object that we will meet in real life. Hypervolume of a four-dimensional region, which is the region under the graph. Under the graph, again, quotations of f of x, y, z. So you see, there's a complete analogy. A single integral of a function g will be the volume or area under the graph of this function, and a double integral will be the volume. A double integral of a function two variables will be volume of something in three dimensions under the graph. And the triple integral of a function f is a hypervolume of the four-dimensional region under the graph of this function. So you have to introduce an additional variable u and say that the graph is given by. So you have four-dimensional space with coordinates x, y, z, and u, and you write u is equal to f of x, y, z. Now, of course, we cannot really visualize it because we can only visualize three dimensions. There is time, so you can think of a region in space-time if you want, and the extra variable u you can think of as time. But still, it's kind of a. So if you think about it, you can imagine this because you can just count. You can look at a certain region in three-dimensional space, and you can count time from certain point 0 to some other point which depends on x, y, z. So that will represent kind of a region in space-time. And what you're calculating is the hypervolume of this region. Now, but still, it's a little bit disconcerting because we don't really have good intuition for four-dimensional space. So it is natural to ask: is it possible to give it a three-dimensional interpretation? Well, we can go back to the double integral and ask the same question there. We can ask: what if f capital, the general function, we know that this integral can be thought of as a volume of the 3D object, but can it also be interpreted in terms of just two-dimensional geometry? And the answer is yes. If you think of this function as a density function, mass density function, then this will give you the total mass of the lamina or some kind of a plate which occupies this region, right? So this is something we discussed last week, the total mass is a double integral, right? So in other words, you can think of this calculation where the function is 1, you can think of calculating the volume, but you can also think of it as calculating the mass. But in a special case, when the density function is 1, if the density function is 1, then calculating the mass is the same as calculating the volume. That's why we get the volume. But in general, the density function could be more complicated. Your object may not be homogeneous. It could have some heavier parts and lighter parts. And you want to kind of average out all of them. You want to find the total mass. And the total mass would then be the integral of that function, of that density function. So from this perspective, you don't have to introduce an extra dimension. If your object